Because the population regression errors are unobservable, we can't test whether or not the exogeneity condition holds. And remember that the exogeneity condition is that the instrumental variable is uncorrelated with the population regression errors. But if we have multiple instruments, then we can perform a test of exogeneity. So let's suppose that we have one endogenous regressor, but we have two instruments. What we can do is that we can compute two different two-stage least squares estimators. These are the betas on the x in the second stage in this two-stage least squares method. And for each of these estimators, we use only one of the instruments. Okay? So what you do is that in the first step, you try to regress x on the first the first instrumental variable, and then you do the same for the second instrumental variable. We call this 2, and that's 2 plus v, 2. Okay, so and now you get two different sets of x hats, and in the second stage you regress the y variable on the intercept plus the slope on x hat from this regression plus u, and you regress y on the intercept plus beta 1 on x hat from this equation plus u. Okay. And we can call these, let's say, star. Okay, because they are not different. The betas on the left side are not equal to the betas on the right side, most probably. Okay, so, and you would then assume that if these two instruments are in fact exogenous, then these betas, the beta 1 and beta 1 star, should be quite similar. To test for this, we can use the J-test. And the J-test actually tests the null hypothesis of the covariance of the first instrument with the regression error term and the covariance of the second instrument and the population regression error term are jointly equal to 0. So in order to, or not in order to, but testing this is just like testing the two estimates. These are equivalent, and this actually tests the beta equal to beta 1 star. So this does actually test what we are asking, are these two coefficients equal? The J-test becomes more tangible if we look at the different steps we have to make in order to perform the test. So our first step is to estimate the equation to stage least squares using both Z1 and Z2 as instruments. So we include both instruments in the equation, even though we are looking for the difference between these instruments, right? Or the difference in the slopes on these instruments. So what we do is we have the first step equation, which is x equals, and we can use pi naught plus pi 1 z1 plus pi 2 z2 plus the w's, right? So this is pi 3 times w, and in this case w is the control variables, okay, or exogenous variables. So we get the sample or the estimate of x hat by performing this regression. And the second step is to use these numbers or this x hat, which is now exogenous, on regressing for the y. Okay, so then we have the intercept and we have the slope on the x hat plus the w's, right? So beta 2, w1, and so on. And we use these, not the residuals from this equation, but we use the, let's see, I forgot some hats here, and there I forgot a d, but we use the slopes here to estimate the residuals based on the true observed value of x. So now we use this model or this model specification from step 2 in order to create some y hats based on inserting the true values of x. Okay, so now we get the residuals from this, and these residuals we are going to check versus the instrumental variables and the control variables. The next step is to use these residuals, the u hat from the two-stage least squares, and we are going to try to explain these by using the intercept plus the slope on the instruments. Oh, this is 1 plus the second instrument plus the control variables or exogenous variables. So this is 1 plus and so on. And what you want to do is perform this regression, and then you would test whether or not these slopes on the instruments are valid or are able jointly to explain some of the variation in the residuals. So your null hypothesis is, in this case, for delta 1 equals delta 2 equals 0. And to find or to test this null hypothesis, you can obtain the F statistic, and in Stata you can use the test function, and the J statistic is just J equals M times F, and the M is the number of instruments. In this case we have 2 instruments, and this is supposed to be distributed, so this means distributed as a chi-square distribution with m minus k degrees of freedom. So at the back of the book, for let's see, Stock and Watson, Introduction to Econometrics, 4th edition, at page 766, then we have the chi-square table. So if we have degrees of freedom equal to 1, because it's 2 instruments minus 1 endogenous regressor, then we have 1 degree of freedom. Then the 5% critical value is 3.84. So if we get a J statistic above this critical value, then we reject the null hypothesis that these 2 instruments are equal, and we can say that either one of them or both of them are not valid instruments. So what we are doing here is that if the Z's, the instruments, are indeed exogenous, which means that they are uncorrelated with the population error term, then they should be also uncorrelated with the residuals from the sample regression. And if they are indeed exogenous, which means that they are uncorrelated with the population error term, then the coefficients of the instruments should be 0. And this is what we tested in step 4 by calculating the F test or F statistic. But it's really important to remember that the J test can only be used if we have more instruments than exogenous or endogenous variables. Okay, so we need to have more instrumental variables than endogenous variables, because in our case we had one x, but we had 2 instrumental variables, which means that in the 2-stage least squares regression, we can first use the first instrumental variable, and then secondly we can use the second instrumental variable, and then we can use the Z1 and Z2 variable to explain x, and then we can check if, or this should be an and then we can actually check if the slopes on these, no, that should be the pi, Okay, so then we can actually test sorry, whether or not these pies, these slopes, are different based on including a different set of instrumental variables. The J-test is quite mechanical and gives us a definite answer, but it's still just a hypothesis test. So even if we calculate the J statistic, okay, which is m times f, and we find that it's below the critical value. Oh my gosh. Let's see here if I can write it properly. Critical value. Okay, so even if we find a small J statistic, this means that we cannot reject, oh my gosh, the null of exogeneity, and which means that we are led to believe that our instruments are actually exogenous, but we might also just be unlucky with our sample. So we cannot definitely conclude that we have exogenous variables, exogenous instrumental variables, even if we cannot reject the null hypothesis.